This video is called the funny cubic formula because the answers it provides are not straightforward and remind me of a practical joke. Let's remind ourselves what a cubic function is. It has an x cubed term, an optional x squared term, an optional x term, and an optional constant term at the very end. Let's see what it looks like when we graph it. As you can see, the cubic equation that we have chosen has 3 real roots. But it could also have only 2 real roots, or at a minimum, it could have only 1 real root. But let's put it away for a moment and focus our attention on solving the general cubic equation. The first step is to set the general cubic equation equal to 0. The leading coefficient a in any cubic formula can be divided out. So let's begin by doing this, and then focus our attention on solving the general cubic equation with the leading coefficient being 1. Our first step in solving this equation is to write the first 2 terms as a perfect cube. This will be a similar process to completing the square in a quadratic equation. The first thing we need to do is remember how to cube a binomial. Let's go ahead and cube this binomial. Notice that we can write the first 2 terms as x plus a cubed as long as 3a equals b, or a equals b over 3. So let's replace a with b over 3 in our equation and simplify. Now let's solve for x cubed plus bx squared so we can replace those 2 terms in our original equation. Notice that now there is no longer an x squared term. However, there is an implied x squared term in our x plus b over 3 cubed term. But if we make a change of variables, for example w equals x plus b over 3, we can truly get rid of any squared term, and we can instead write an equation in terms of w. This new equation is a cubic equation in w, but without a w squared term. So we're making some progress. Let's let p be the coefficient in front of the w to make things simpler, and let's let q equal the constant term. To make some further progress, we make a guess at what our answer will look like, and it will turn out to be a successful guess that our answer will be in the form of u plus v, where u and v are 2 separate terms. So we'll make the substitution w equals u plus v. So let's substitute u plus v back into our cubic equation for w and cube out the first term. Then we factor out 3uv from the middle 2 terms. Here we notice that u plus v can be factored out of 2 terms, and so we do this and arrive at this expression. This form of the equation suggests 2 conditions on u and v to make the left side identically 0. We must have 3uv minus p equal to 0 identically, and u cubed plus v cubed plus q must equal to 0 identically. To solve this system of 2 simultaneous equations, we solve for v in the left equation and insert the result into the right equation. Next, we multiply every term by u cubed. We can then see that this is simply a quadratic equation in u cubed. We can see this by imagining that u cubed equals x, and we can therefore solve this equation by using the quadratic formula. Let's clean this up a little. And notice that we can choose either the plus sign or the minus sign in this expression. We substitute this back into the previous equation to obtain a result for v cubed. With a little manipulation, we see that v cubed has the same form as u cubed, although the plus and minus sign are reversed. This means that whatever sign we choose for u cubed, we must choose the opposite sign for v cubed. We take the cube roots so we can solve for u and v, and then remembering that w is just the sum of u plus v, we substitute back into the expression for w. The plus and minus signs in this expression for w must be opposite, and so without any loss of generality we can choose one plus and one minus, since the other way round yields an identical result. So let's choose the plus sign for the first term and the minus sign for the second term. Let's bring back the expression for x in terms of w, so we can write out the cubic formula in all its glory. Now, I promised you this cubic formula was funny, and I don't want to disappoint. It's a real practical joker. So let's see how this funny formula works. Let's use our example from before, and remembering our expressions for p and q, let's substitute in a value of b of -10, c of 31, and d of -30, and find out what p and q are equal to. Since the cubic formula uses p over 3 and q over 2, let's divide by 3 and 2 respectively. Now let's start plugging everything into the cubic formula. We start with b, -10, p over 3, 7 over 9, and q over 2, -10 over 27. Simplifying the radicand to -1/3, we find our result for x. But wait a minute, shouldn't our result for x be either 2, 3, or 5? Or better yet, shouldn't the answer for x somehow be 2, 3, and 5 all together somehow? Well, the funny cubic formula has expressed our answer in terms of the square root of negative numbers. So I told you the cubic formula was a real practical joker. In order to get a real answer out of it, we have a little more work to do. We begin our work by extracting a -1 out of the square root sign and writing it separately as the square root of -1. We will call this expression I, which stands for imaginary number, because the square root of -1 has no answer in the real number system. Let's go back to the general form of the cubic formula for a minute to see what we've done. If p over 3 cubed is greater than q over 2 squared, we switch the order of these two terms, factoring out a -1. This is what we did in our example. So we can rewrite the general form of the cubic formula in this way. So as you can see, the cubic formula in this form has a real part, the -q over 2, and also an imaginary part that's being multiplied by I. We call a number that has a real part and an imaginary part a complex number. It's funny that the cubic formula is forcing us to handle complex numbers when the three roots of our example are 2, 3, and 5, just simple whole numbers. So we must take the cube root of this complex number, and there's a little trick that helps us do that. We write the real part of the complex number as a cos theta, and the imaginary part of the complex number as a sine theta. A and theta are just new variables that will replace p and q for the moment. In order to find a in terms of p and q, we square both equations and add them together, and use the fact that cos squared plus sine squared equals 1, a trigonometric identity, in order to find out a in terms of p and q. Then we substitute this result back into the first equation to find theta in terms of p and q. Now we go ahead and replace p and q in our cubic formula with a and theta. The radicand inside the first cube root is cos theta plus I sine theta, and the radicand inside the second cube root is cos theta minus I sine theta. These two radicands are both perfect cubes, as I will prove to you now by using some trigonometric identities. I'm going to show that the first radicand is the perfect cube of cos theta over 3 plus I sine theta over 3. And so the first thing I'm going to do is cube out cos theta over 3 plus I sine theta over 3, and eventually show you that it equals cos theta plus I sine theta. The first trigonometric identity I'll use is that cos 2x equals cos squared x minus sine squared x. So cos 2 theta over 3 is equal to cos squared theta over 3 minus sine squared theta over 3. The second trigonometric identity I'll use is that sine 2x equals 2 sine x cos x. So sine 2 theta over 3 is equal to 2 sine theta over 3 cos theta over 3. Expanding out, we then use the trig identity that cos x1 plus x2 equals cos x1 cos x2 minus sine x1 sine x2. So cos theta over 3 plus 2 theta over 3 equals cos theta over 3 cos 2 theta over 3 minus sine theta over 3 sine 2 theta over 3. And finally, we use the trig identity that sine theta over 3 plus 2 theta over 3 equals cos theta over 3 sine 2 theta over 3 plus sine theta over 3 cos 2 theta over 3. We finally find that cos theta over 3 plus I sine theta over 3 cubed is equal to cos theta plus I sine theta. So let's go ahead and replace the radicand inside the first cube root with our perfect cube, cos theta over 3 plus I sine theta over 3 cubed. To deal with the second radicand inside the second cube root, we simply replace theta with minus theta in our identity, and we find that the second radicand is also a perfect cube, namely cos theta over 3 minus I sine theta over 3 cubed. So let's go ahead and replace the second radicand with this perfect cube identity. The cube and cube roots cancel each other, and we also find that the imaginary parts of our expression cancel each other, and we're left with real values only. Substituting back in our values for a in terms of p and q, and theta in terms of p and q, we find our final result for x in terms of b, p, and q. To see how this expression works, let's go back to our example, with b equaling minus 10, p over 3 equaling 7 over 9, and q over 2 equaling negative 10 over 27. Plugging all these things in, we find a numerical value for x. In order to evaluate this expression for x, we first must evaluate the arc cos. Now, arc cos is multivalued. In our example, on a unit circle, this corresponds to an angle whose x-coordinate is 0.54. This corresponds to an angle of approximately 1.00 radians, but it could also correspond to an angle of 1.00 plus 2 pi radians, or 1.00 plus 4 pi radians. We're going to ignore negative angles in these cases because they produce the same results as the positive angles. So we can represent the arc coast value in our expression as 1.00 or 1.00 plus 2 pi or 1.00 plus 4 pi. Or in short, 1.00 plus 2 pi n, where n is equal to 0, 1, or 2. We could go higher with n, but it would simply be reproducing the values that have already occurred with 0, 1, and 2. When we let n equal 0 and punch everything into our calculator, we get x equals 5. When we let n equal 1 and punch everything into our calculator, we get x equals 2. And when we let n equal 2 and punch everything into our calculator, we get x equals 3. So incredibly, this crazy looking expression for x yields our three results, 5, 2, and 3. Remember, we developed this particular equation when we assumed p over 3 cubed was greater than q over 2 squared. In that case, like in our example, we get 3 real roots. If instead q over 2 squared is greater than p over 3 cubed, there will only be 1 real root. In that case, we switch the radicand terms back to their original positions and absorb the square root of -1 back into the radicand sign. We will draw the corresponding graph for this case on the left. I will write an example equation corresponding to this graph up above, and we can calculate p and q just as we did before. But let me tell you, the funny cubic formula has another trick up its sleeve. Now b equals 0 in this new cubic equation because there is no x squared term. So we can get rid of most of the parts of the p and q expressions. When we substitute in what remains, we find that p equals 1 and q equals -6. Now remember I told you that this new cubic equation has q over 2 squared greater than p over 3 cubed. But let's go ahead and check to see if that's true, just to make sure we're using the right formula. When we substitute q equals -6 and p equals 1 into the inequality, we find that q over 2 squared is equal to 9. But p over 3 cubed is only equal to 1 over 27. So 9 is greater than 1 over 27, so this equality checks out. We should be using this cubic formula. Let's substitute these values into the cubic formula, along with the value of b, which is 0, because there is no x squared term. Now let's do some simplifying. We multiply inside the square root by 3 over 3, so we can get 81 in the denominator, which is a perfect square that we can take out of the square root. An 11 squared can also be removed from the square root. We are left with a final expression for x that is not easily simplified. It is the sum of cube roots of nested square roots, and it is unclear what it may equal. But if you punch it into your calculator and press the equals button, you get exactly 2. This is the other funny practical joke of the cubic formula. It gives you these exact answers, like 2, but in forms that are completely unrecognizable. If you already knew the answer was going to be 2, there is a way to simplify the expression for x so that you get exactly 2 in a recognizable form. But without guessing the answer beforehand or something equivalent, there is no other way to simplify the expression. It really is a funny cubic formula. Thank you for watching.